Good morning, and thank you for the opportunity to present my dissertation. My name is Manisharan and the title of my research is Semantic Aware Quantization for Pre-trained CNNs. In simple terms, the deep learning models today are very powerful, but they are often too large and computationally expensive to run efficiently on a real-world devices such as mobile phones or edge systems. To address this, we use a technique called as quantization. Quantization helps reduce the model size and computation, but the traditional approaches often treat all the parts of the model too similarly. In this work, I explore a smarter approach where the most important parts of the model are preserved more carefully while the rest are compressed more aggressively. The goal is to reduce the size and cost without losing the meaningful performance. Before going into the details, let me first walk you through how the presentation is structured. In this presentation, I will cover 7 key parts. I'll begin with the background and motivation behind the work, followed by the main insights from the literature review. Next, I will define the research problem along with the aim and objectives. After that, I'll explain the methodology, including the process framework, dataset models, and evaluation approaches. I will then present the results and discuss what they mean. Finally, I'll conclude with the main contributions, limitations, and the direction for the future work. So, overall, the presentation follows a simple flow from the problem to the solution to the results and then to the insights. Now that I have outlined the structure, let me begin with the background and motivation behind the research. Deep learning models, especially CNN, are widely used in computer vision tasks such as image classification, object detection, semantic segmentation. They achieve a very high accuracy and are used in many real world applications. However, these models are often large and computationally expensive. Because of this, it becomes difficult to deploy them efficiently on devices such as mobile phones, embedded systems, drones, or other low precision environments. To address this, techniques such as quantizations are used. Quantization reduces the precision of numbers in the model, which helps reduce memory usage, computational time, and energy consumption. But there is an important limitation. The traditional quantization methods usually treat all the parts of the model equally or focuses only on numerical sensitivity. This means they do not distinguish clearly between the features that are critical for the prediction and those are less important. As a result, important features may be compressed too aggressively, which can reduce the performance and also affect interpretability and relatability. So, the motivation for this research is to go beyond that limitation. Instead of comparing everything in a similar way, we can identify which is most important in the model and preserve it more carefully during the compression. Now that we have understood the motivation, let's look at how the work fits into the broad research context. To understand this work, it helps to look at how quantization methods has evolved. First, we have uniform quantization where the same precision is applied across the entire model. This approach is simple and efficient, but it assumes that all parts of the model are equally important. Next, we have the mixed precision quantization where different layers are assigned different bit widths. This is an improvement because it recognizes that some parts of the model are more sensitive than other. However, most existing models still rely mainly on numerical measurements such as gradients, statistics, or error. They do not directly consider whether a feature is important for the model's accurate decision making process. This is where my works comes in. I introduce semantic aware quantization where the model is compressed based on how important each feature is to its reasoning. So the key shift here is moving from purely numerical compression to more meaningful semantic guided compression. Building on this context, now I briefly summarize the key insights from the literature. From the literature, I identified 5 key themes that shaped this research. First, the fundamentals of quantization, especially post training quantization, which is widely used to improve the model efficiency without recurringly retraining. Second, mixed and adaptive precision methods, which show that selective bit allocation often performs better than uniform compression, but still mainly relies on numerical sensitivity rather than the semantic importance. Third, explainability techniques such as GradCM and LRP, which provide the insight to which the features are most influential in the model decision making process. Fourth, the silency guided compression, which suggests that interpretability signals can be used to guide optimization although this area is still relatively underexplored. And finally, energy aware and sustainable AI, which highlights the growing need for practical resource aware model deployment. A key observation from the literature is that efficiency and interpretability have often been studied separately. This reveals a clear research gap, the lack of integrated approach that combines semantic understanding with post training quantization. This gap is what my research aimed to address. Based on these findings, I'll now define the core problem this research focuses on. The main problem in this research is that most quantized models focus only on reducing model size and improving efficiency. They do not consider which part of model are actually most important for decision making. Because of this, important features such as key filters or layers may be compressed just as much as the less relevant ones. This can lead into a drop in accuracy, and it also can make the model less interpretable and less reliable. This issue becomes even more important in computer vision tasks where preserving the meaningful spatial and semantic features is critical. So the research gap is clear. There is no particular post-train quantization approach that exactly preserves semantic importance during compression. This gap directly motivates the development of the semantic aware quantization or SAQ framework. Based on this problem, I'll now outline the aim and objective of the research. The main aim of this research is to develop a semantic aware quantization framework for pre-trained CNNs. In simple terms, the goal is to make the model compression not only efficient but also more aligned with how the model actually make the decisions. To achieve this, I defined 5 key objectives. First, to review existing work in quantization and interpretability. Second, to use the techniques such as GradCM and LRP to estimate feature importance. Third, to design a method that allocates precision based on this importance. Fourth, to apply this approach across different tasks including classification, detection, and segmentation. And finally, to evaluate the framework against standard methods such as FP32 and uniform quantization. Overall, this objective moves from understanding the problem to build a solution and then to validate it experimentally. Now, I'll explain the core contribution of this work, the proposed semantic aware quantization framework. We begin with an input image which is passed through a pre-trained CNN. Instead of directly compressing the model, we first use the GradCM and LRP to understand which parts of the model are most important for the prediction. This relevancy signals are then converted into a saliency score and normalized so that the different components can be compressed more fairly. Based on these scores, we assign different bitwise mapping. Components that are more important receive high precision, while less important components are compressed more aggressively. This produced a compressed deployment ready model that still preserves the key decision making pathway. For example, if a model is detecting a dog, the feature focusing on the dog itself can be preserved with high precision, while less important background details such as sky or grass can be compressed more strongly. Also, because this is a post-training approach, it works directly on pre-trained models without recurring retraining, which makes it more practical for the real-world deployments. Now that we have seen how the framework works, let's look at the dataset and the tasks used in this research. To evaluate the framework, I used 3 well-known benchmark datasets, each representing a different computer vision task. First, CIFAR10 for image classification. This is a simple balanced dataset which makes it useful for controlled experiments. Second, MS COCO for object detection. This is more complex dataset with multiple objects and realistic scenes, so it helps both recognition and localization. Third is Pascal Vogue 2012 for semantic segmentation. This is the most demanding of the 3 because it requires pixel level prediction and strong preservation of spatial details. So overall, these datasets allows evaluation across increasing level of complexity from classification to detection to segmentation. Now that I have introduced the dataset, I'll briefly explain the models and experiment setup used in this study. In total, I conducted 15 experiments using 5 models for each task. For classification, I used ResNet 18, MobileNet V2, EfficientNet V2, DenseNet 121, and ShuffleNet V2. These represent different design approaches ranging from standard deep architectures to lightweight and efficient networks. For object detection, I used SSD Lite MobileNet V3, Fast RCNN, RetailNet, Focus, and SSD 300. This includes both lightweight and more complex architectures as well as different detection strategies. For segmentation, I used Deep Lab v3, UNet++, uh, PSPNet, FPN, and MANet. These models capture the spatial details and contextual information in different ways. The key idea behind the selection was to test the framework across wide range of architectures so that the SAQ is not limited to a specific model type but can be evaluated more broadly across different scenarios. Now I'll explain the central technical idea behind this work, how the saliency is used to guide the bit allocations. First, we extract the saliency information using GradCM and LRP. GradCM uses gradients of the targeted class with respect to the convolution feature maps to identify which regions are the most important for the prediction. LRP complement this by propagating relevancy backward through the network, giving a more fine-grained view of how different neurons contribute to the final output. These relevancy signals are then converted into a quantitative saliency score at the filter or the channel level. The scores are normally between 0 to 1 so that they can be compressed consistently across the network. Next, we apply a rule-based mapping strategy to assign the bit widths such as 2, 4, 6, or 8 bits. This is essentially a form of adaptive mixed precision quantization where the high saliency components receive the high precision and the low saliency components are compressed more aggressively. Unlike traditional methods that rely mainly on numerical sensitivity and weight statistics, this approach directly incorporate the semantic importance into the compression process. For example, in the image, the model focuses on the dog as the main object. The highlighted regions shows where the model is paying the most attention. Filters that can capture the important features such as the dog's face, body, edges receive the high precision while less relevant regions such as background can be compressed more aggressively. So fundamentally, this framework shifts quantization from a pure numerical optimization problem to a semantic guided compression strategy. Now that I have explained how the framework works, let's look into how it was evaluated. To evaluate the framework, I used both predictive and deployment related metrics. For classification, I used accuracy and F1 score. For object detection, I have used the mean average precision. For semantic segmentation, I used the mean intersection over union. But predictive performance alone is not enough for the comparison study. So I have also measured the comparison ratio, latency, energy consumption, and interpretability retention. Comparison ratio shows how much the model size is reduced. Latency reflects how fast the model runs. Energy consumption indicates how efficient the model for the real world deployment. And interpretability retention checks whether the model still preserve the meaningful saliency behavior after compression. So overall, the evaluation balance performs efficiency and interpretability, not just accuracy alone. Now I'll discuss the key quantitative results of the study. The table compares the performance of FP32, SAQ, and uniform quantization across the three task group. Starting with classification, the performance across all three models is very similar overall. However, the SAQ shows more variation depends on the model architecture. In some models, it preserves performance very well, while in other, the gain are less consistent. For object detection, SAQ performs more consistently. It preserves mean average precision very close compared with the FP32 and uniform quantization, while also achieving better compression. For semantic segmentation, the results are even stronger. SAQ achieves the highest compression gain while maintaining almost identical mean intersection over union values. This suggests that the saliency grade quantization works practically well in tasks where the spatial and structural information is especially important. It also shows that not all tasks benefit equally from semantic aware quantization, which is an important insight from the study. So overall, SAQ matches the standard methods very closely in predictive performance, but provides clear comparison advantages, especially in detection and segmentation, while classification results depends more on the model architecture. Now, I'll go one more step deeper and interpret what these results actually mean. The first key takeaway is that SAQ performs better in object detection and semantic segmentation. In this task, the important information is closely tied to spatial regions such as objects, boundaries, and contextual structures. Because silencing methods capture these regions effectively, the framework is able to preserve the most critical pathways during compression. Second observation is that classification results were more dependent on the model architecture. Models such as ResNet 18 respond well, while others such as DenseNet 121 and some lightweight models showed weaker or less consistent improvements. To summarize these findings more clearly, here are the main overall results. First, SAQ was able to preserve performance very closely, especially in object detection and semantic segmentation. Second, the strongest improvements were seen when semantic pathways were clearly identified and stable. This supports the idea that interpretability can be meaningfully guided compression. Third, classification results were more variable, which shows that the effectiveness of SAQ depends on both the task and the model architecture. And finally, SAQ improves the balance between the compression and interpretability by preserving the most important parts of the model rather than compressing everything equally. So, in one sentence, compression becomes more efficient when it is guided by semantic importance rather than only by numerical simplifications. To understand this more clearly, let's now look at how the findings differs across the three task types. For classification, the semantic importance is usually concentrated in deep layers. This means the silency grade compression can help, but the impact depends strongly on the model architecture. For object detection, relevancy is more distributed across both regions and localization components. Because of this, preserving this pathway becomes more important, and SAQ shows more consistency benefits. For semantic segmentation, the relevancy is even more distributed across the network, including the context modules, feature fusions, and refinement strategies. This helps why segmentation shows the strongest improvements with SAQ. So, a clear pattern emerges as the task becomes more structurally complex, the values of semantic aware compression increases. This shows that SAQ is not just a compression technique but a framework that becomes more effective as the model reasoning becomes more spatially structurally dependent. Finally, I conclude with the main contributions of this work. To conclude, this dissertation developed and evaluated semantic aware quantization framework for pre-trained CNNs. The main contribution is in the integration and interpretability into the post-training mixed precision quantization. Instead of compressing the model purely based on numerical factors, the framework uses silency to preserve high precision in decision critical components. The study shows that not all parts of the model contribute equally to its reasoning, and therefore they should not be compressed equally. By using techniques such as GradCM and LRP, the framework creates a more meaningful and targeted allocation of precision. The results demonstrate that this approach provides a better balance between the compression and interpretability, especially in tasks such as object detection and semantic segmentation. More importantly, this work highlights that efficiency and interpretability are not complete goals. In fact, interpretability can actually guide better compression decisions. So one key takeaway from this project is that compression should not be judged only by how much we reduce, but by whatever we are preserving what truly matters to the model. Finally, I briefly discuss the limitations of this work and possible directions for the future research. Like any research project, this study has few limitations. First, the experiments were limited to selected benchmark datasets and pre-trained CNN models. While this provides a broad evolution, it does not cover all real-world scenarios. Second, the work focuses only on CNN and does not include transformer-based models, which are becoming increasingly important in this computer vision. Third, the framework mainly uses GradCM and LRP for estimating the semantic importance. Other explainability methods can provide additional or more detailed insights. Looking ahead, there are several directions for the future work. The framework can be extended to more datasets and new architectures, especially the transformers. So, while the work demonstrates the potential of semantic aware quantization, it also opens up opportunities for further research in efficient and explainable model compression. That brings me to the end of my presentation. Thank you for your time and attention. I hope this presentation has clearly shown the motivation, approaches, and key findings of my work. To end with one message, the model compression becomes more meaningful when it preserves the semantic reasoning, not just numerical efficiency. Thank you.